First, why do we care so much about this small archipelago off the coast of Ecuador? Well, that can be most easily answered by examining the event that truly put the Galapagos on the map. In 1831, Charles Darwin, fresh out of college, moved back in with his parents. Like many of us, he had no idea what he would do with his life. Unfortunately, Starbucks wasn't hiring, but one of Darwin's pals hooked him up with a gig as a naturalist. The only catch, the job would actually cost him money. Luckily, old man Darwin could afford to literally ship his son off for a few years, and on December 27, 1831, Darwin boarded the HMS Beagle to set sail across the Atlantic on a 5-year adventure. The Beagle was bound to sail around the tip of South America and on around the globe. The Beagle made many stops along the way, and Darwin hopped off to do naturalist things, like sample the wildlife. And I mean literally sample. Having rounded South America, the Beagle headed west and made its fateful stop in the Galapagos Islands. It was here that Darwin would make the observations that led him to his theory of evolution. His ideas have revolutionized the world and made the Galapagos one of planet Earth's most sacred sanctuaries. But what if Darwin could have somehow sailed through a black hole and arrived in the Galapagos, let's say 5 million years ago? What would he have seen? Simply ocean. The Galapagos Islands are fairly young and only appeared between 3 and 5 million years ago. How do islands rise out of the sea, you say? To understand that, we'll need to learn some basic geology. But we've done a lot of work so far, so how about a moment of zen? The first concept we need to discuss is plate tectonics. According to this theory, the Earth's outer layer, or lithosphere, is made up of moving plates floating on a molten mantle. These plates are made of material from the crust and upper hard mantle, and their interactions give rise to everything from deep ocean trenches to mountain ranges. The plates are given motion by convective currents in the mantle beneath them. Hot mantle rock from near the core rises and cools as it approaches the crust, then circulates and eventually sinks back down to the core as it condenses and becomes heavier. The plates are also driven by gravity, as ocean crust is driven down beneath continental crust, pulling its plate along behind it. Plate tectonics has shaped the geography of the world as we know it. But how does this concern the Galapagos? The Galapagos Islands are located on the Nazca Plate, which is west of South America and bordering the Cocos Plate. The Nazca and Cocos plates are moving apart and eastward, forming a mid-ocean ridge called the Galapagos Spreading Center, and subducting beneath Central and South America. This plate movement has been absolutely critical in the formation of the islands, as you will see in a moment. But first, a segue. Alright, now back to work. The next concept we need to discuss is the formation of volcanoes, specifically from hotspots. Why? Because the Galapagos Islands are volcanic islands. A hotspot, or mantle plume, is an upwelling of especially hot rock from the core mantle boundary. Theoretically, this hot rock slowly rises through the mantle and, rather than cooling and solidifying, it melts and expands as it rises. This melting is due to decreasing pressure surrounding the molten rock. The rising of the mantle plume is eventually stopped by the lithosphere. Here the melt, or magma, begins slowly rising through small channels in mineral grains, and eventually gathers in a magma chamber just a few kilometers beneath the surface. When enough pressure builds, this magma can burst through. Over time, successive eruptions build the volcanoes we see in places like Hawaii, or the Galapagos. So, what happens when we mix plate tectonics and hotspots? As we now know, tectonic plates are constantly in motion, but hotspots are fixed points. For example, The Hawaiian hotspot and the Galapagos hotspot have remained in the same place relative to one another, even though the tectonic plates above them are moving. As this hypothetical plate moves over a hotspot, a volcano forms. As the plate continues moving, this volcano will eventually become extinct and erode away, as new volcanoes form in its wake. The oldest volcano in a chain reveals the direction of plate movement. But wait, you say, the Galapagos Islands aren't linear. That's true, and to see their pattern of plate movement, we have to look under the sea. Here we see the Carnegie Ridge, an underwater ridge formed as the Nazca Plate passed over the Galapagos hotspot. As evidenced by the two other ridges seen here, the Cocos and Malpelo, the Galapagos spreading center has moved north and south at various points in the 20 million years since the hotspot is theorized to have formed. The oldest seamounts in the Carnegie Ridge are continually subducting beneath the South American plate, and one day, the Galapagos themselves could subduct beneath this plate. Now, that was a lot of geology, but what does it mean for the islands as you can experience them today? Well, the habitat on each island was essentially predetermined by the minerals deposited on them in the eruptions that formed them. For example, the northern islands contain a higher percentage of mid-ocean ridge basalt than the southern islands, which contain more of the mineral mix unique to the hotspot. The islands' mineral compositions, along with their topography, give each one a unique habitat that allows certain species to adapt and thrive.